Buenas tardes. No grabamos las preguntas, siempre me pasa lo mismo. Ok, entonces vamos a compartir aquí.
Profe, fallamos. Yo acabo de conectarme y solo alcancé a hacer la pregunta de el 2. Quizás podría dar una pequeña ayudita con el 1.
A ver.
Perdón, profe.
Ya voy a ver aquí, tengo la tarea. Guardé la tarea.
Ah, en la pregunta 1 yo vi un error, profe. O bueno, no sé si era error a propósito.
Error a propósito. No tiendo a hacer ese tipo de cosas.
Era solo la dirección de la flecha.
Es que el chiste de la 1 es que no están permitidas.
Exacto,
Sí, por
no,
eso no
es
sabía
decir,
si es que era
cuáles
error a
son.
propósito.
No, digo, exacto, por eso. Hay algunos diagramas que son cero, otros que no son. Entonces, la cuestión es identificar, ¿no? No, la intención no es poner todo, se me perdió la tarea. Ya, déjame ver si la encuentro otra vez por aquí. Zoom toma control de la computadora de una manera. Homework 2. Esta. Aquí está.
Ah, profe, en la última pregunta también faltaban algunos hats en los operadores. Bueno, creo que es lo de menos, pero igual falta.
Así, eso sí es típico, pero
Ajá.
que se me olvida algún hat.
Pero sí se entendía.
Ok. ¿Están viendo la tarea ahí? No.
No, solo está
El cuadrito
el archivo.
Stop share. Así lo encuentro aquí ahora. Aquí está. Ok, entonces, ¿cuál era la pregunta?
A ver, por ejemplo, del 1, en ambos diagramas, por ejemplo, el primer diagrama, la bolita esa de ahí que está, como está en el sentido horario, no puede ser, ¿no es cierto? Porque estábamos teniendo dos partículas al mismo tiempo, ¿verdad? En el primero,
No,
en el que
aquí en el primero sí que puede ser, este es el error que quizás está mencionando
sí,
anteriormente. O sea, esta flechita tiene la intención de que está yendo para atrás en el tiempo, ¿no? No
sí,
para
debería, ¿no
adelante.
es cierto?
Sí,
Y
pero
por eso
por
no
eso
está.
siempre la dibujo pegadita de la interacción, ¿no? De la línea de interacción. Entonces, ese no es un problema en principio ahí.
Ya. Y la otra
Ujú.
tendría que tener en esa parte que está curva, digamos, tiene la interacción, el fotón se emite, luego tenemos una línea recta, luego se emite otro fotón en ese que parece el oyster,
Exacto,
pero en la parte del oyster tendría que estar al revés, ¿no es cierto? Tendría que estar apuntando hacia abajo.
Esa es la propósito que decía.
Sí,
La
O sea,
flecha,
eso podrían,
la
exacto,
flecha
podrían
de la,
estar los dos intercambiados, ¿no? Pero de
claro,
todas
eso
o
maneras
el de
eso
la
no,
derecha,
de todas maneras
el
eso
de
no
la
hace
derecha,
mayor problema en el caso. Sí, sí, tienen
esa
razón que
flecha,
esto he podido dibujarlo al revés, ¿no? De ponerle la
era hacia
flecha
abajo.
bajando,
y,
exacto, bajando
y justo
eh,
esos peros son los que hacen que, por ejemplo, lo que diga eso, the following diagrams are not allowed,
ujú,
really, ¿no es cierto? Eh,
correcto.
¿Cómo le haríamos
Ay,
cómo le haríamos para probar que no son, o sea, podemos decir con palabras que no está mal,
Bueno,
pero, y también le
dos
estaba
cosas.
intentando,
Yo les enseñé dos maneras de hacerlo, ¿no? Una con simplemente con un argumento general
medir
al
la
respecto
altura.
de que no podías tener el mismo momentum por encima y por debajo del KF en un mismo diagrama, ¿no? Ese era un argumento, ¿no? Y el otro era haciendo el segmento, por ejemplo, agarrando simplemente el segmento de la interacción, donde están tratando de ver si las flechas están entrando y saliendo correctamente de la línea de interacción, pueden entonces hacerlo en segunda cuantificación. Les enseñé cómo hacerlo también, ¿no? En clase. De que entonces, cuántas partículas hay en el sistema, cuáles se destruyen, cuáles se crean, y entonces ver que si el resultado da cero o no da cero. Si da cero, entonces el diagrama no es posible, y si no da cero, entonces es una contribución finita. De esas dos maneras se podían... Pero digamos aquí, mi idea era que se dieran cuenta desde el punto de vista del argumento general, ¿no? Por ejemplo, que yo no puedo, si le asigno un Q a una de esas líneas, ese Q tiene que estar o por encima o por debajo, ¿no? Y entonces no puede estar simultáneamente por encima y por debajo del nivel de Fermi.
ok, ok, ok,
¿Ok?
nos toca respetar el nivel de Fermi.
Sí, no, pues, digamos, es una cuestión matemática, ¿eh? Si es un Q, escoges un Q, entonces el Q para una línea que va para adelante tiene que estar por encima del nivel de Fermi, y si la otra línea va por detrás no puede estar etiquetada con el mismo Q, ¿entiendes? Con el mismo momento.
Ok,
Ese
ok,
argumento lo vimos ¿ok?
en clase.
Ajá,
Yo tengo una última duda, profe.
ajá.
En el 3C,
13. Ajá.
en ese, únicamente nosotros debemos decir que el KL es mayor que el otro y por esa razón solo es como que le hacemos el expectation value, porque ahí sale como que directo, o sea, no sé qué nomás se hace ahí, porque nosotros en clase hicimos con un potencial específico y es
Claro,
básicamente, y se les dejó el
aquí
descriptivo.
no estamos aplicando ningún potencial. Deja de dejar el focus
Ajá.
Entonces, aquí no estamos diciendo nada respecto al potencial, ¿no?
Ujú,
Entonces, muestre show the form of the interval KL, the effective. Bueno, exacto. Entonces, esto es simplemente partir eh, fíjate que pongo aquí el superíndice Hartree, de manera que es simplemente el término KL y KL que no incluye el
ujú,
KLLK.
ujú,
Entonces, de la forma general de la interacción de la, eh, de la interacción de dos cuerpos, ver cómo escribir el potencial efectivo como el valor de expectación de ese potencial. ¿Se acuerdan que cuando escribimos la aproximación de Hartree-Fock vista desde el punto de vista de la ecuación de Schrödinger?
Sí, le unimos todo y hizo
Exacto,
un
entonces
potencial que quedaban.
quedaba esto ensanduchado como el promedio de este potencial, ¿sí? El valor de expectación de ese potencial. Ok, entonces esto eran todas, precisamente yo tomaba una partícula de referencia que separaba del resto, y entonces todas las demás partículas quedaban por debajo del nivel de Fermi o por debajo del nivel de esa partícula, por ejemplo, en una estructura atómica, y entonces esto era la suma de toda la carga que estaba por debajo, digamos, en la carga promedio que estaba viendo la partícula de Hartree, ¿no? En la aproximación de Hartree. Eso, digamos ahí, vean las notas de clase, cuando yo escribí la expresión de para la ecuación de Schrödinger se ve cómo sale este término precisamente de la interacción de dos cuerpos, ¿ok? Entonces se ve este potencial promediado en la función de onda de una sola partícula, ¿ok? Entonces vean ese pasaje de las notas para que ustedes vean cómo, a qué me refiero acá.
Ya, ya. Es que a mí me
Clase
salieron
9 minutos a la primera hora, creo que fue.
Ajá, ya sabes hasta el minuto y todo.
Justo
Ok,
estaba también haciendo el S
ok,
y sí sale esa
sí,
cosa de ahí
claro.
del...
Ajá.
Claro, usted le llegó es lo que está esto ahí de las dos funciones de onda. Bueno,
Ujú,
las dos funciones le dejó en delta conjugado y cómo es el conjugado y el no conjugado, pero al final es lo mismo. O sea.
ujú, correcto, sí. Muy bien.
Ya, gracias.
¿Otra pregunta? ¿Todo bien?
No, en mi caso no.
Ok, muy bien.
Gracias.
Profe,
Chévere.
sí sería plausible que, digamos, si es que tenemos alguna otra duda que nos vaya surgiendo a lo largo de hacer este deber, podemos escribirle un mail o
Sí,
alguna
sí,
cosa
sí,
por el
claro,
estilo, no hay
escriban,
problema.
escriban, escriban y cuando digamos ya no haya más preguntas, se declara ya lista la tarea para entregar. ¿Ok?
Muchas gracias, profe, por
Muy
ser tan
bien,
comprensivo.
chévere, está bien. Importante es que aprendamos el material. Ok, entonces vamos aquí con la clase. Bien. Ok, entonces, today I wanted to tell you just a few more details of how we can write operators, not necessarily Hamiltonian operators, but generic operators like the density. All right, okay, writing, let me put the title here, writing physical quantities in second quantized form, second quantization. Okay, so I'm going to give a few more examples here. Okay, from time to time I have to use these, otherwise I'll forget. Should be able to write these things, put these things perpendicular automatically. Okay, so for example, the density, we did this last time, and just review it so that we are in sync. So we had for example, the density operator. Okay, remember that this in principle is not an operator because we write it. This will be just the wave function. Okay, the modulus square of the wave function. That will be the density. Okay, this will be the number density. Okay, so this will be in first quantized form. But then, in order to write in second quantized form, we converted the wave functions into operators. So we write it like this. So this will be first quantization. Okay, so we're going to be able to write very interesting quantities now, like currents, for example, also in second quantized form. So we turn the operator into the wave function into operator form, and we write it like this, second quantized form. Okay, so this will be second quantized. Okay, so how do I express the second quantized form of the wave function? Well, we say just the wave function operator is now written in terms of the wave function itself. Okay, so we choose some basis. some basis functions. These basis functions are here. Here's the R dependence, and we put now the corresponding operator. So now this would be the second quantized operator. Okay. So then we just substitute this into the expression. So we'll get now rho operator. This is the density operator. Okay, so this applied to a ket in the occupation space formalism will give me something like the number of particles, right? So this will be then sum. We have two wave functions, alpha and beta, and then we have C alpha dagger, C beta, okay? Phi alpha dagger, okay? Phi beta. Okay, so this would be the second quantized form of the density, okay? The expression of the density in second quantized form. Okay, you can do a very nice thing. For example, if you integrate now the density operator in space, okay, you know that this will give you, if this is a number density integrating over space, this will give you the number operator. Okay, so this will be now the sum over alpha, substituting the previous expression. Okay, this expression. And then we have the integral over dr3, and then we have phi alpha, okay, dagger, phi beta, var, and then we have C alpha, P beta, which do not involve any R dependence. So you know that this now we can apply. We chose a basis here to expand the wave function in second quantized form. So this will be the delta alpha beta, okay? And so we end up with the regular operator, which will be sum over all the occupations of C alpha dagger, C alpha, okay? And we know that this is the number of particles in state alpha, and the sum over all states gives me the total number of particles, and this will be the operator for the total number of particles. So this is a consistent way to write the density operator in this case. Okay, is it clear how we do second quantization of the wave function then? Okay, how we write it in terms of the creation and annihilation operators. Okay, we can do this then, for example, for another type, another operator we will use in transport, for example, the current density operator, okay? The current density operator will be written like this. It will be 1/2 this is in first quantized form. So we would have for example, if we have different charges associated with the particles, okay, then we would have the velocity, okay, times r minus ri plus, that would be it. Well, if we write it, this we can write it like this. Okay, so just so that we take care of the commutations between operators. So this would be the current operator. It would depend directly on this delta function in space, and then the velocity operator in this case. Okay, so this is a current density . Okay, we can write the velocity, for example, the velocity that is involved here can be also written as the momentum operator. Okay, if we have some particle over m. Okay, and this we write, for example, in first quantized form. We can write it like this. We have here, and we write that we sandwich the momentum operator between the wave function. So this would be the expectation value of the momentum divided by m. I put a 2 here because I want to consider two permutations of this. So if I separate this like this, then we can think of two possible orderings of this operator, and we put it like this. So we symmetrize it like this. So this will be the complex conjugate. Okay? So if you do this in first quantization, right, you have 1 over 2m, and then you have psi, and then this is h over I, rad, psi, okay, plus now the conjugate of this, h over I, rad, psi, everything daggered, psi. Okay? So this is just, remember this is just I write it in these two ways and divide by 2. This is let me put it here with another, so you notice it, it's a symmetrization. Okay?
The second term is the Hermitian conjugate, really?
Right, so this dagger is the Hermitian conjugate of P psi, okay, P psi. So I just changed the order of this, right? So if you have AB, okay, something like this, AB is B, A dagger. Okay, so you switch the orders and you dagger both terms. Okay, so this is exactly.
And in this case, the psi is the basis, the function basis that we choose.
No, this is the wave function. This is directly the wave function. Yes, yeah.
Okay.
Okay, we'll express it in terms of a basis later. Okay, so this is more general expression. Okay, so okay, so let's take out all the factors. Now we have a factor of I here, and we have a factor of minus I here because of the conjugation. So you finally get H over 2 mi, and you get psi dagger. I took all the factors of I, and here I should have used another notation, but remember that I'm using the ith. I have the ith, and here should be I, here should be I, and here should be I and I here. Okay, so this should be gradient I, and then psi plus with a minus now, minus a gradient I psi dagger, okay, psi. Okay, so that would be the expression in first quantized form of the velocity operator, okay? So, and we're going to second quantize it in the following page. I just wanted to remind you also of a relationship for obtaining the velocity, okay? The velocity, you know, that is also equal, recall, okay? And we're going to use this relationship later. Recall that V is R dot, okay? And you know how to take derivatives of with respect to time in quantum mechanics. You write them as 1 over h, the commutator of the Hamiltonian. Let's suppose this will be the Hamiltonian with the with R. Okay, that will be the way to calculate the time dependence of the position or the velocity. Is just the commutator with the Hamiltonian. Okay, you learned this in at least quantum mechanics 1 at least. So if we assume that the Hamiltonian is now the free Hamiltonian, this will be p squared over 2m, and then this will be r, okay? And then you can work out very easily that this is going to give you just p over m, okay? Which is what you would expect for the velocity operator in terms of this. This, from the classical point of view, this is obvious, but it also comes out from the quantum mechanical relation, okay? Is this clear to you? I mean, how to obtain this? So you can expand this very easily by using just a commutator between R and P, okay? So you know that Rp is equal to is equal to IH, okay? And you just use it here and demonstrate that this is true. Okay, so with those, yes, with those two comments, then we can build a bunch of operators here. Let's build here first our velocity operator and our current density operator. Okay.
Teacher,
so yes.
Can you repeat the meaning of nabla I?
Of what?
Nabla I.
Nabla I. Remember that in the vector form of your momentum, right? This is the first quantized form of the, okay?
Mm-hmm.
Okay, so this is the first quantization form of the momentum. That's what I put here. Okay, I just missed the putting the vectors everywhere, right? Okay.
Profe, and the minus in the 5 line.
This minus here?
Yes.
This is because we have the conjugate here, right? We have the denominator here, we take it out, and now we have the conjugate of the I, right? So we get the minus sign.
Yeah.
Okay.
Teacher.
Yes.
Teacher, why the wave function doesn't have a subindex I?
Because it's just a wave function. This will be, for example, the momentum of some particle I, right? And this is the full wave function of the system.
For all the particles again. For
all the particles.
okay.
Mm-hmm. Okay. Any other question? Okay. So let's write now the current density. Here I'm going to put, for example, this could be another. So this some index I put here could be a particle index, okay? But here, for example, I'm going to choose now a particular component. So we're writing here a vector, okay? Let's write a particular vector, and this generally I can choose I again, okay? So this will be the, let me define ith, okay, component of current density. Okay, so let's write now the expression we had before. So we had EH times 2 divided by 2mi, and then we put the form of the wave function, right, in second quantized form. So second quantization. Okay, this will be the sum over alpha and beta. Okay, and then we have C alpha, dagger C beta, and then we have the first ordering of the operators here in second quantized form. So we have psi dagger nabla psi. Okay. Okay, so we have psi phi sub alpha, corresponding to this operator here at R, okay? And then we have nabla, and now I here, okay, because of the ith component. So this will be the ith one of the components of the nabla operator, which is just one of the derivatives, okay? And then we have phi beta r, okay? So this will be one term, and then the other term will be minus, okay? Will be C alpha, again, C alpha dagger, C beta. We have the same ordering here because here psi dagger comes before this one, and we have to keep the ordering once we turn this into a second quantized form. Okay, so we get C alpha dagger C beta, and then we get the other ordering for the wave function. So this is no longer the daggered one, function of R, nabla, the ith component corresponding to this component here, and we have alpha R dagger. Okay, so that would be the way you write this second quantized form, and this will be in real space, right? This everything is written in real space here. Okay, so if we go to Fourier space, okay, now this I should write the function of R. Okay, now we can write this the ith component now in Fourier space. Okay, we get then E over H. Now we have lots of practice doing Fourier transform, so I don't have to be so explicit. Okay, anyway, we have questions. Okay, remember that what we do here is we multiply both sides by e to the iq dot r. Okay, multiply both sides and integrate over all real space. Okay, and integrate. Okay, so imagine you multiply this side by e to the iqr, integrate over all space, and do the same on the other side. So what we are obtaining then is C alpha dagger, C beta, we can take as a common factor. Here is going to be the integral in space. Then we have phi alpha dagger, phi alpha conjugate alpha r. Okay, then we have nabla of I by beta bar, okay, e to the I minus q of r. Yeah, I forgot here, this should be minus here. Okay, so this is why I got the minus here, and then we have the other one would be, this is all under the same integration, okay? This is just a continuation of this. Okay, phi beta r nabla I phi alpha dagger e to the minus. Okay, and we close parenthesis here. Okay, so what we can do now is that we choose, okay, we choose basis, okay? So for example, free particle. Okay, so now we know that phi alpha, okay, phi alpha is going to be e to the I alpha vector r over some norm, okay? And we substitute here wherever we have alpha or beta, we substitute for this form, okay? We know how to do that, okay? And let me skip here so that we can have an exercise for you to do. So you substitute that into the expression, the free basis, and you should get this expression. So this is a good practice for you to see your understanding of the Fourier transform. So you get alpha beta, C alpha dagger, C beta, and then you get I beta, so I, okay, omega And put all the factors here, although they cancel. So you can follow. You get beta alpha plus q, okay? And then you get plus I alpha I omega comes from the delta integration, okay? Delta beta alpha plus q. Okay, so this you should get just by substituting those exponentials inside the integral here. And remember, you have this factor of IQ. You have this minus alpha here because you have the conjugate. You have I plus plus I beta dot r in this case. So combining those expressions and combining them here, also you will get this expression here. Okay, so finally, jumping another step so you can have fun with the deltas, you should get in the end this expression here. Okay, one delta gets rid of one of the summation indexes here, and you should get this expression. Okay, so that's this is the expression, the second quantized expression for current density in Fourier space. What did I do there? It was Fourier space. Okay, so save for a few steps that I leave to you. I mean, this would be the way to use this second quantization of the wave function in order to obtain the now the second quantized operators for quantities like and I seem to have missed here.
Teacher.
Yes, I already. What happened to the I? Right?
And the 2
and the
in
2
the denominator in the first term.
Oh, because we have two terms here. You see, you have both the factors of. Let's see. No, you're right. There should be a factor of 2. There's a factor of 2 here. Okay, because these don't add to 2. They have different. Okay, so I have beta. So if I have the ith component in Q space, let me not get ahead of myself here, because I would just wrote the most general expression at the end. So this should be 2 alpha I plus
Q.
Let me see one second here. Right. Let me think of one second. I have some confusion here. Beta j, right? Because we take just the derivative with respect to j. Right. It's the same delta. Okay, so I guess I should write the most correct form here would be, right, so you get beta here. So this would be, this I is canceling with this one, so we eliminate it from here, so we get these two cancel. Okay, we get beta, so I plus ice, okay, times delta beta alpha plus q. Yeah. No, still I would have beta here. Okay, and we do this step by step then. Okay, do you follow here? So up to here, up to this point, this is correct, right? Okay, so now if, what would be the statement that I would make here? So we have E over H to M, okay? So what I could say, what can I say about the components? Okay, so I guess this means that when beta is equal to alpha plus q, then this would imply that each component, this is, so the equation by components would be this one, right? So this implies that I can write this as alpha, and I write everything in terms of alpha. So, here I would strictly have a beta still, okay? And here we would have a beta is equal to alpha plus q, okay? And here we would have that this is 2 times alphas I plus q I, okay? And now this is why I didn't have the 2 in the denominator. So we extract a factor of 2 from here, and we have this relation. Okay? Do we agree? Now everything is kosher? Correct?
Profe, sí,
Yes?
gracias. Sí, está bien.
Okay. Okay, very good. So this would be now my expression. If we want to generalize this now to any component, so we have J vector, it would be very easy because now we just eliminate where we had the expression of the components, okay? And this will be dagger C alpha plus Q. Then this will be just alpha vector plus Q vector over 2. Okay, this will be just the sum of the components with the corresponding unit vectors in Q space. Okay, so this will be the final expression for my second quantized form of the current operator. Okay, do we agree? So now we have a general system to build any operator, any physical operator we want in second quantized form by using the second quantized form of the wave function, okay? We can do this in many other examples that are going to be useful for any, you know, any work that your advisor puts to you. For example, the polarization operator. Start writing in black, polarization operator. Okay, if you want to measure the polarization of your quantum mechanical system, then you would have to do it quantum mechanically, of course. So if you okay, again, you write your polarization, electrical, this electrical polarization, okay, electrical polarization, not magnetic polarization. Okay, so this is generally when you have some object here and you have some negative charges on this side and you have some positive charges on the other side. So you have a certain polarization, you have an electric field like this, and you have a polarization also in this. Okay, so the polarization just tells you how the charge is distributed in space, okay? So this will be the classical definition would be the integral over all space where there is charge, okay? And this will be the vector times, okay, times the charge density. Okay, that's the definition, okay? Of this is not a vector, so this is a scalar. I don't need to put that dot there. All the charge distribution is telling you if there's a separation of charge like here, we will get a finite P. If the charge is uniform, then we get 0 from here because this would be just an even function of space times an odd function of space integrated over the whole space will give me 0. Okay, so we can use here the same prescription. Now we go to what the prescription should be. So still in first quantized form, this would be, okay, times psi, okay? And then we can, so this would be just the expectation value of the position vector, okay? First quantized, and then we can second quantize by second quantize. Okay, by converting these wave functions into operators, okay? So we get R, and then we get dagger, operator, dagger, operator, and then we use the particular basis. So we get integral dr3 of R, and then we have the sum alpha beta T alpha dagger C beta, and then we phi alpha. Okay, so that will be the form of this, and now we, you know, push the space integral through the sum. So we get the sum over alpha and beta, and we get the operators on this side. Okay, and we get now the integral in all space R by, okay, and this will be just the expectation value in the first quantized form, which was generally how we wrote these things, right? So this is the expectation value of the R coordinate, okay, integrated over the whole space, and depending on the distribution of charge, which is given by this, we get the different forms. So this will be written as the average alpha beta, okay, times this. This will be the final form of our polarization operator. Okay, so you see it's very easy. This way of prescribing second quantization is maybe the most useful one, the most generic one. Okay, any questions about this? Okay, I have another example that I will put to you in the homework, but I just wanted to do one now in real space, a discrete Hamiltonian, for example, a tight binding Hamiltonian. Okay, another example. Okay, this we will soon in the final section of the course, we will see lots of how to build these tight binding Hamiltonians and lend themselves to analytical solutions. Okay, tight binding Hamiltonian. Okay, and we could have something like this. For example, a kinetic term, which we have dealt with in our first homework. So we have delta plus J, dagger J, okay? And then we can have something like this, 1/2. And we have an interaction, which depends on the product of two number operators, okay? And some coupling constant, okay? So let's suppose you have something like this. Of course, you remember that you have to write this plus complex conjugate, okay? But the exercise will be pretty much the same for both, okay? C is J, right? And this is a fixed. This is just a fixed displacement, okay? So how do we write the current? Okay, so the current. This is a very sort of sneaky way of writing the current density. Notice that you have when you're building a polarization, right? So you start with uniform distribution of charges, right? So this is uniform charge, okay? And then you apply an electric field, for example, okay? And then you imagine that this is going to polarize all the positive charges on one side and the negative charges on the other side, okay? So, but this happens in time, right? You apply the electric field and then, you know, all the positive charges start to migrate into one direction and the negative charges start to migrate into the other direction, okay? In time, polarizes in time, okay? So here P is equal to 0, the polarization is equal to 0. That's not rho, that's P. Okay, and here P is different from 0. Okay, so you can think of the current density as some resulting from a time dependence of the polarization. Okay, of course, when the polarization starts here, you have a current while you're setting up the polarization, and when the polarization reaches a maximum, okay, a steady state, then this is 0. So the current, we have it only in the middle, okay? It's only the time dependence of this, okay? But the interesting thing is that if this is true, then we can use now the definition I told you before of how to obtain the time dependence by commuting with the Hamiltonian. So this will be H times P. Okay? So now instead of having to solve, for example, some kind of equations of motion, I just have to do this commutator here. And I have already the Hamiltonian, and I have the definition for the polarization. So I can just write this one out. And I will just write to you the first line of this. So you have an exercise to do in this. So this is just an exercise in second quantization, in commutation relations, okay? So this will be just, first we write the Hamiltonian, so Cj plus dagger Cj plus the interaction term Ij and I and J, okay? And this will be Vij, this is just a number, regular number, and this commuting with, okay, the discrete form of the polarization operator. Okay, so polarization operator we can write like, okay, so this is the charge, okay, charge, okay, density, and this will be the position of that charge density. So I have, for example, this will be just an electron in one place, a positive charge in another place, and we multiply by its position and sum over all possible positions. So this is a position label. Okay, and we have to do this. This is also the positions of the charges, and this is also a position label here. So we have to now do the commutation between these two guys. Okay, so remember that we have these are fermion operators, so we're talking about electrons. So we have to take into account use fermion commutations. Okay, commutation relations. Okay, and remember that this is just a number operator. These are number operators, so this is automatically going to commute with any combination of other number operators here. So we can just omit directly the commutation between these two, and you only have to do the commutation between these two. This is not the number operator, so it doesn't commute with this guy, and we have to work out that commutation explicitly. Okay, so I'll just put to you the final result, and for sure it will be not all that intuitive from the beginning, but if you work, just follow your nose with the commutation relations, you should obtain this. Okay, so okay, do and add to homework. Okay, number 4. Okay, which is not yet posted. Okay, and you will get extra credit in case you miss some points, or you miss some points from the homework number 4. Then we can add this demonstration to that, and you will get extra credit for that. Okay, any questions about this? I mean, this is just substituting, okay, the Hamiltonian and the definition of the polarization operator into this expression, just expanding this and doing all the commutations. You should get this this form of the second quantized form of the polarization of the current density. Okay. Okay, good. Okay, so let me make another comment here. Comments on phonon interactions. Okay, this is just before we're doing the final exercise of this section, which is before starting on the Holstein model. Holstein Polaron problem. Okay, so so you remember that you discussed we discussed in solid state 1 the importance of anharmonic terms. In the Hamiltonian. Okay, remember that in the harmonic approximation, okay, in harmonic approximation, okay, phonons do not see each other. Okay, that means that you cannot have processes like this. Let's represent in a kind of a Feynman diagram form. If you have a process like this, okay, one phonon is coming in here, the other phonon is coming in here, okay? So this phonon has, for example, wave vector q2, and then this has wave vector q1, and then they both collide and a single phonon comes in. Remember that phonons don't work like fermions. Phonons are massless bosonic particles, so they can appear and disappear. Okay, so this is not allowed in harmonic approximation. Okay, in the harmonic approximation, the Q2 lives forever, Q1 lives forever, and Q3 will not appear if it's not there already, okay? Because remember that we have the Hamiltonian is just the sum over all the Q's, okay? And we have H omega, some frequency, and then we have the creation annihilation operator. And this is just the sum over all these Q values here, okay? So if we have a certain number of Q's, it's the Q1 and Q2s is included there, they will live forever. They're eigenstates, okay, of the system. So you cannot make, there's no way in this Hamiltonian to make them disappear and to make another Q vector appear. So the only way we can do this is to include some terms like this in the Hamiltonian. Okay, for collisions to occur, we must have terms like this. We have like B3 dagger, B2, B1, right? And then we have, for example, one phonon in state 1 and one phonon in state 2, okay? So this would be, right, this would be just the two phonon states coming into the collision, right? So Q1, Q2, Q3. Okay, so these will be the two ones. So this is the initial state. This is the timeline. Okay, so they exist before colliding, and then this destroys one. So this one gets destroyed. This destroys the other one, and then this makes appear the third momentum. Okay, so this the Hamiltonian. Okay, Hamiltonian should be able to do this. Include this process. Okay, and clearly this Hamiltonian does not have any such terms. I should have put, instead of A, I should have put B. I put B here just to say that they are bosonic, bosonic operators. Okay. So is it clear? Is it clear that we need to have these kind of processes here in order to have contemplate a collision like this? To have so to have the phonons see each other. Okay, and remember that this is a really important process because otherwise we have no, okay, without phonon collisions, we don't have thermal conductivity, okay, or thermal expansion. And we know these things happen in nature, right? So we should have, wrote that horribly there, thermal conductivity. Okay, or thermal expansion. So we need to include these type of terms in the Hamiltonian. So this will be the unharmonic effects. Okay. So how do we include that? Well, we need to include a term which is now going to be the phonon interaction term, which is the in the harmonic expansion, we would have a term like this: 1/3 factorial, then some R and R prime. Okay, I know we didn't. I avoided at all costs doing this big expansion. Okay, in class because it was just an exercise in vector calculus. Okay, but it would be of this form here. So let me it will be nice to write it out so you can see what the harmonic term looks like. Okay, then you have J. Okay, and then finally, this is the cubic term, K, R. Okay, and then this would be the potential interaction between sites R okay, it's R prime divided by okay, so this would be the first unharmonic term. Okay, and the harmonic, okay, the harmonic term, and be 1/2 factorial, and again you have two real space vectors, and now you only have two indices here, and you would only have, yes?
In the derivative, should be the third derivative.
Yeah, third derivative.
Okay.
Okay, so now instead of having 3 factors here, then you only have 2. Or this will be the harmonic. And second derivative. Okay, so this is the harmonic term. Okay, so you see this is just a Taylor expansion. Okay, in vector form, or in the representing the in terms of the indices. Okay, so this will be now the third derivative of the potential. The first derivative is 0 because they're expanding around the minimum. Okay, and then we have this. The harmonic term will be the first contribution with which we generate, okay, you see this quadratic in the displacement. So this will be generate my harmonic Hamiltonian, okay, and then this will be the correction, okay. So, and this will be the first term that generates phonon-phonon interactions. Okay, so how will we write this term in second quantized form? Okay, this term in second quantized form, and this is just a lot of algebra, but it's very understandable on the basis of what we have been doing. Would be, now we have 3 Q vectors, okay, because it's a three particle process, okay, so 2 particles coming in, 1 particle coming out, that you will see in second quantization very easily. So we have now that this will be some big coefficient that depends on the three Qs. It doesn't matter what the form is, but the important form is that this displacements are written in second quantized form in this way. So we have A Q1 dagger minus A Q1 times A Q2 dagger minus AQ2, AQ3 dagger minus AQ3. Okay. I forgot. There's a minus sign in each of these here. Okay, so minus Q1 minus Q2 minus Q3. Okay, so you just have to go back to the expressions we had in just in 1 dimension. These are the generalizations to 3 dimensions. Okay, so and now we have, you see that we can have terms like AQ1 times AQ2 times AQ3, so we can make 3 phonons appear, okay? Or we can make 1 appear and 2 disappear, okay, with the corresponding signs, and so on. So we can have a bunch of processes there. Specifically, we can have one like this, okay? Processes. You can have one like this, a Q1 dagger, a Q2 dagger, okay? A Q3 dagger. So interaction makes 3 phonons appear. Okay, so of course this has to obey momentum conservation. So it would be something like this, for example. So we would have, for example, something like this, and then the other phonon. Okay, so that the momentum is conserved. Okay, but you can also have processes like this: A, Q1 dagger, minus Q2, minus Q3. Okay, so you could have something like this. So a process like this, just so I represent also the direction of the momenta. This is minus Q2, minus Q3, okay? And then this coming into a Q1. Okay, or the other way around if you want. So two of these disappear in the process and this one appears in the process. Okay, so kills two phonons and creates one. Okay, so this is the one. This is the way in which now this type of interaction, this an harmonic term in second quantized form, which would be this kind of a process. Okay, generates now my phonon collisions. Okay, phonon. Okay, I know I'm being very qualitative with this, but I mean, this is we already developed the tools in order to do this. So it's a matter of just sitting down and working out the problem. We did the diagrammatics for phonons the last class in one dimension. So that this would be the natural extension in 3 dimensions with only the complications associated with vector algebra. Okay, there's just one last comment I wanted to make on these collisions, that you know that these would be normal processes. So this is just stating in second quantization things you know from solid state 1. So normal processes are the process where we have Q1 is equal to just referring to this previous process that I have here, this process generated by this would be Q1 is equal to 2Q2 minus Q3. Okay, this will be the normal process, and also we have that we have H, and we need to conserve energy, of course. So we have omega of Q1 is equal to omega of minus Q2 plus H omega of minus Q3, okay? And this depends on the dispersion of the phonons, okay? So we have a phonon dispersion omega of Q, okay? Phonon dispersion. Okay, but we have also the Umklapp processes. Okay, and with this I finish the class, so I'll show you why these Umklapp processes are very important. So these are actually the processes that generate thermal conductivity. So now if I pass these two vectors to the other side, we would have something like this. And this, instead of being 0, is going to be a vector, okay, of the reciprocal lattice. Okay, so remember that these are responsible for thermal conductivity. Okay, so let's stop here for today, and tomorrow I'll show you why these processes generate thermal conductivity with a very brief argument, and I'll show you that these processes do not degrade the current, the current of phonons, which is a current of energy, right? It's a current of heat, the current of phonons. So this process will not generate a degradation of that current, okay? But this process will. So we need to have a certain type of process, okay, that generates a degradation of the current density of phonons so that we can have thermal conductivity, okay? And that will be the final comment I make on the phonon-phonon interactions, so that we can go on to the Polaron problem. Okay, so next class. Okay, thermal conductivity. And the Holstein model. Okay, any questions? We extended a little bit more than we usually do, but we had lots of questions at the beginning, so. Okay, so don't hesitate to ask questions about the homework. I will include all the corrections that you found today. They're important because I didn't draw many details of the homework correctly. Okay, so but don't hesitate to ask me any other questions you might have, so that we can turn in this homework this week and start working on the number 3. Okay.
De acuerdo, profe.
Okay. Okay, so see you tomorrow then.
Sí,
See
profe.
you, teacher. Thank you.
Bye, teacher.
Bye bye.
Chao, amigos.
Ciao.